Okay, so in this video, we'll talk about the pigeonhole principle and do a couple of examples. The general form of the pigeonhole principle is the following. It's that if you have k times n objects, or more than k times n objects, and you place them into n classes, then it must be true that some class has more than k objects in it. And this is a pretty obvious statement if you think about it, right? Let's put some numbers into this just to give you an idea. Let's say you have 4 classes, right? And let's say that you have, let's see, k times n, so n is 4. You have more than 16 objects, right? Just to make this statement work. So let's assume we have 17. Okay, so what happens if we have 4 classes and 17 objects that we want to distribute among the classes? Well, okay, so you can think of the 4 classes as these 4 boxes: upper left, upper right, lower left, and lower right. Okay, 17 objects, so let's start putting them in. Maybe you could put the first object here, and then the second object in the same box, maybe the third here, and so on. And you can keep on doing this, but it should quickly become apparent to you that you're not going to be able to put all 17 of them without one of the boxes getting more than 4 things. Right? So k equals 4 here. I guess I should have picked a different number just to better illustrate the statement, but one of the boxes has more than 4. And it's quite easy to prove this statement, actually. You just need to do it by contradiction, right? So if you assume that each class has at most k objects, well, you should be able to complete this proof at this point. And now the form of the pigeonhole principle that you'll probably be using more of in this course is that specific form for k equals 1. Right, so it's this. When you basically plug in k equals 1 into the previous statement, this is exactly what you get, right? So this is a corollary of the previous statement. Is that if you have more than n objects and you place them into n classes or boxes, then one of the class will have more than one object, right? And this is an even more obvious statement, right? And the reason why this is called the pigeonhole principle is if we have more pigeons than pigeonholes and you try to stick them into these pigeonholes, then you must have at least 2 pigeons sharing a pigeonhole. And so I'll give you an example again. So what if n is equal to 7, right? So let's say we have 8 objects and 7 classes. Well, that means one of the classes will have more than one object. And in fact, note here that we're not saying that there's exactly 2 in one class, right? It's entirely possible that among these 7 classes, all 8 objects fall into one class, right? That doesn't contradict the statement, right? This class has more than one object, but it's possible. We can have 2 classes that have more than one, right? It doesn't matter. All the statement says is that one class has more than one. And in order to apply the pigeonhole principle, really you have to think about the following questions. First, what are the pigeons, or the objects? Next, what are the pigeonholes, or my classes? And finally, how do you pick, right, what the pigeons and pigeonholes are to guarantee that the conclusion of the pigeonhole principle results in you having the property that you desire for the problem? Okay, that's kind of abstract here, so let's work on this particular example. You have 11 natural numbers, right? Any set of 11 natural numbers. And you're asked to show that there must be a pair of them whose difference is divisible by 10. Now you can check this if you want, right? Give a set of 11. What happens? So, I don't know, 85, 13, 447, 2, 5, 61, 70, and so on, right? And until you get 11 of them. Now, even if I don't finish listing this all out, I already see that I have two numbers such that when you take their difference, you have a number that's divisible by 10. And this should give you an idea here. So in fact, why don't you pause the video for now and figure out, try to think about what the pigeons and pigeonholes are here. Okay, so pause the video now. Okay, so did you figure it out? Why we ended up with a number here that was divisible by 10 was simply because it ended with a 0, right? And so really what this tells me is, in order for me to get the desired property, right, I need to have two numbers with the same last digit in my list of 11. And that's sufficient, right, to guarantee that desired property. Right? But wait a minute. I have 11 natural numbers. How many possible last digits are there for any natural number? Well, there are 10 possibilities, 0 to 9. And that's my clue there, right? My pigeons, well, they're going to be the numbers themselves. And the pigeonholes are going to be boxes where the numbers are placed to the box corresponding to what its last digit is. All right, so let me write that down properly here. So let the 11 natural numbers be the pigeons and place them into pigeonholes labeled 0, 1, 2, all the way to 9 based on what their last digit is. Okay, and here's the argument. By the pigeonhole principle, which we'll abbreviate as PHP here, one pigeonhole must have at least two pigeons. Right, so this is just the standard form of the pigeonhole principle with k equals 1. Well, okay, now that we have one pigeonhole that has two pigeons, in our scenario here, what that means is at least two of the numbers from that list of 11 share a last digit, right? Because this assignment of pigeons to pigeonholes, right, depended on what the last digit was. If two numbers shared a pigeonhole, that means those two numbers share a last digit. And I don't really care what the last digit is. It could be 3, it could be 9, it could be 7. It doesn't matter. Because now I know that if I take their difference wherever they are, right, so their difference is going to be divisible by 10. Right. And that completes the proof for this particular example. Okay, so let's look at another problem, one that is slightly different here. Here you're also given a set of integers. They're not natural numbers anymore. Here they're just integers, so they're allowed to be negative. And you're given 6 of them. And the statement is, there is a pair among them whose sum or difference is divisible by 8. So again, you can check if you want. Take any 6 integers. So let's see, -3, 10, 5, 17, -9, -23, oh, and that's 6. Can we find 2 integers here whose sum or difference is divisible by 8? And I immediately see something here. The difference of -3 and 5 is exactly 8. Right, so that is our pair here. That satisfies the desired property. There may be others too. Yeah, so in fact 17 and -23. The difference is 40. And that's also divisible by 8. But it's not as obvious as the last question. Right? And there's an or here as well, which means really we have 2 properties that we want, or that we want either of them to hold. Either we want the sum or the difference to be divisible by 8. So how would we do that here? Again, think about the question. What are your pigeons? What are your pigeonholes? And how do you make that assignment of pigeons to pigeonholes such that getting 2 pigeons in the same pigeonhole is this desired property? Now here's a little tip. Whenever you're asked to prove an or statement, right? So in general, say you were asked to prove the statement P or Q were true. Well, one way you could do that was by assuming P is false, then proving that in that case, Q must be true. Right? Because if P were true, then you wouldn't have to do anything else. You'd be done. But if you assume P is false and you prove that in that case Q is true, right, then that is exactly what you need to prove that or statement. So let's do that here. Let's assume that there is no pair among these integers whose difference is divisible by 8. Okay. What does that mean for us? Well, basically this means all 6 of these integers have distinct remainders, right, when we divide by 8. right? Because if two of them had the same remainder, say 19 and I don't know, 43, right? These both have remainder 3 when you divide by 8. When you subtract them, the remainders cancel, and you're left with something that's evenly divisible by 8. So now we're at a point where we've assumed that all of them have distinct remainders. So let these 6 integers be my pigeons. My handwriting is really bad here. Let these 6 integers be my pigeons and assign them to these pigeonholes. Zero, 1, 7, 2, 6, 3, 5, and 4. 5 pigeonholes here. And you're placing the pigeonholes, you're placing the pigeons in the pigeonhole that corresponds to their remainder. And remember, they're all distinct here, right? So what's going to happen is, if you place 6 integers into these 5 pigeonholes, then one of the pigeonholes will have 2 pigeons. And what this means for us is, well, that must be one of these 3 in the middle. And now summing those 2 integers will give you a number that's divisible by 8. Right, so just to give you a recap here, what happened was we assumed that there is no pair among them whose difference is divisible by 8. Because if there was, then you'd be done, right? You already have what you need. But if all of them have distinct remainders, and there are 6 of them, well, what are the possible remainders? It's 0 to 7, and they're here. And we've labeled our pigeonhole so that the first pigeonhole has 0, the second has 1 and 7, and so on. We just place these numbers into these boxes based on what their remainders are. Since there are more integers than boxes, one of these pigeonholes would have 2 numbers, right? To be specific, one of these 3. And it doesn't matter where it is exactly, you just add them together. If it's 1 and 7, 2 and 6, 3 and 5 for the remainders. If you add the 2, then you'll get something that's exactly divisible by 8.